Log on, tune in, find out. Another good idea from Cambridge.
Improve the entropy for finite Markov chains.
Yes, thank you very much. Thank you very much for inviting me to Cambridge. It's a great pleasure to be here and give a talk. Okay, so I will speak about some recent approach that we started developing with the aim of bringing to the discrete setting some tools and techniques from the theory of optimal transportation, which have been very successful in a continuous setting. Okay, so let me maybe start by mentioning, say, a classical result in this topic. So in the continuous setting in Rn, there is a very nice connection between three objects, which was discovered in the second half of the 90s by Jordan, Kindler, and Otto. So the three objects are the following. So first is the heat equation. So dt rho equal to Laplacian rho. The second well-known object is the entropy functional. So say the Boltzmann-Shannon entropy. Which is well defined by the usual formula. H of rho is the integral of rho x log rho x dx for probability measures rho on Rn. So and you see I'm always, at least for the moment, identifying probability measures with their densities. So this is for rho probability measure or densities on Rn. Okay, and the third object is the Wasserstein metric. So the L2 Wasserstein metric. This is a metric, so a distance function on the space of probability measures, which is defined using some kind of optimal transportation problem. So the idea is the following. So you take, you have two probability densities, like this, and your task is to move the mass, which is distributed according to this distribution, from here onto this other distribution. Yeah? And well, this is not for free, so your task is to do it in such a way that you minimize a certain cost function, and the cost associated with moving a unit of mass from here to here is the square of the distance. Yeah? So you're trying to find an optimal transportation plan which maps this distribution onto this one. So to say it more mathematically, so the Wasserstein distance between two densities is the infimum of the integral over, say, Rn cross Rn of x minus y squared gamma xy. So you take the infimum over all measures gamma on the product space, so Rn plus Rn. You're taking the infimum over all measures which have the property that the marginals are rho naught and rho 1. Yeah? So gamma has marginals rho naught and rho 1. Yeah? So it means if you take the image measure of gamma onto projection onto the first coordinates, you get rho naught, and if you take the image measure onto projection of the second coordinate, you get rho 1. Okay, so these are the three objects.
Just to be sure, this is the metric itself or the square?
Yes, of course. Thank you. This is the square. Okay, so these are the three objects, and the theorem, which was then proved by Jordan, Kindler, and Otto, in 1998 was the following. So let me maybe first quote it as a kind of a slogan. So the heat flow is the gradient flow of the entropy, so of the functional h, with respect to the metric W2. Okay, so that's the statement of the theorem. So of course I should explain what this statement means, because it's not obvious what it means to be a gradient flow in this setting. So let me maybe as an intermezzo. So what can we say about gradient flows on Rn? So if we take some function phi from Rn to R, which is smooth and convex. Well, what does it mean to be a gradient flow? Well, a function u which takes values in Rn is a gradient flow if the following equation holds. d dt of ut is minus the grad phi of ut. Okay, so this is the usual notion of gradient flow, but you can also reformulate this in slightly different terms, which makes it possible to adapt this notion also to this setting. So it turns out that this is equivalent to the following inequality, to saying that 1/2 ddt of the norm ut minus y squared is less than or equal phi of y minus phi of ut for all elements y in Rn. Okay, so that's an equivalent formulation of the usual gradient flow formulation. Okay, and you see that this one is much more useful for our purposes, because this formulation does not involve taking any gradient, so there's no gradient in the second formulation. And there's no derivative of some function which takes values in the space Rn. There's just a derivative of some scalar valued function, namely the square of the metric, so of the distance between ut and y. Okay, so this second statement also makes sense over here. So what they showed is that if U solves the heat equation, or if rho solves the heat equation, then then you have the same inequalities. Then you have that 1/2 times ddt, and now there's the Wasserstein distance square of rho 2 nu is less than the entropy of nu minus the entropy of rho t. And this holds for all new probability measures, at least for which this makes sense, for which the entropy is finite. Okay, so this is actually not the way they originally proved it, but this is an equivalent statement of being the gradient flow of some functional. Yes. So that's true. So there I mentioned that's the equivalent for convex functionals. And here there's also some convexity around. So the entropy is convex along geodesics in the Wasserstein metric, which is a famous result by McCann. Yes, on flat space, and also on Riemannian manifolds, but then the modulus of convexity is determined by the Ricci curvature. Okay, so that's to say the classical result in Rn. And well, this result was really one of the starting points for many developments in the theory of optimal transportation. So, for instance, you can use this approach to prove some interesting functional inequalities like Lobsowicz inequalities or Talagrand inequalities. So there are many applications that I cannot not go into here, of course. Another remarkable thing is that the formulation here really uses almost nothing about the underlying space. Yeah? So we do not use the linear structure of the space and also not the differential structure of the space. Yeah? So you only need to be able to define the Wasserstein metric. And well, for defining the Wasserstein metric, you only need the metric on the underlying space. Yeah? Then you can put a square of the metric over there. And for defining the functional, you only need to have some kind of reference measure. Then you can define the entropy. Yeah? So this is potentially well, useful in much more general settings. And in fact, many extensions of this result have been proved during, say, the past 10 years. So this remains true in Riemannian manifolds, has been proved by Erbar. It remains true also in Finsler manifolds by Ota and Sturm with this. There are infinite dimensional examples like Wiener space. Tang Xiao and Sturm proved this in this kind of setting. So many different examples. And just last week, Ambrosio, Gili, and Savare, they posted on the archive a preprint where they really showed the equivalence between this gradient flow formulation using the entropy and the Wasserstein metric on the one end, and on the other end, the more traditional approach using Dirichlet forms. And they proved this in a quite general setting of very general metric measure spaces. Okay, so this is quite a big topic now and has been well developed, and there's well, much information about it in the books by Villani and also in the book by Ambrosio, Gili, and Savare. Okay, so that's like the starting point of what I would like to talk about today. So the naive question which I would like to pose is, well, can we do anything like this also if the underlying space is discrete? Yeah? So all these results which I just mentioned, they say nothing about what happens if the underlying space is discrete. Okay, so maybe let me just sketch the framework which I would like to discuss. So which is just very basic and standard. So let's just consider a finite set. X a finite set. And on this finite set, I consider a Markov kernel. So some function k from x cross x to r plus Markov kernel. Well, that just means that that if I sum kxy, if I sum over all y, then I get 1. Yeah? So these, you can think about these as being the transition probabilities of some kind of Markov chain, and this is the probability of moving from x to y. Okay, so what we will assume that, well, the standard thing that k is irreducible. That means just that you can reach any given point in the space, starting from any other point using this Markov kernel. And under this assumption of irreducibility, so how do I do it? Well, so this implies that there exists a unique invariant probability measure which I call pi. It just means that pi of x is equal to the sum pi of y, sum pi x kxy. Oh, so this is a natural natural reference measure in our setting, and it's uniquely defined. And it has also the additional property that, that it's strictly positive. Yeah. So pi x strictly positive for all x. Okay, so maybe let's... Okay, so the only real assumption that I need to make is the following. That's some kind of symmetry assumption. So I assume that this k is reversible. That means that, well, kxy times pi x is equal to kyx times pi of y for every x and y. Okay, so this is, for instance, the case if you consider a random walk on a graph, which is a good example to have in mind. Okay, so this is our setting, and in this setting we would like to do the same thing here. So we can define the analog of the three objects over here, maybe the heat equation, the entropy, and there's also a Wasserstein distance. So these three objects, so the heat equation now becomes like this. So let me write it as a semigroup. So the heat semigroup, say HT, is just e to the t k minus identity. Yeah, so in this example of a random walk on a graph, k minus identity is just the Laplacian of the graph, and then it's the natural heat semigroup. So this is nothing but the continuous time Markov semigroup associated with this setting. Okay, then there's the entropy. So the relative entropy. So maybe to fix some notation, I will now always work with the densities because it's somehow more convenient than working with measures. So let me write h of rho is the sum over x, pi x, rho x, with rho x. And this is for rho in the space of probability densities. And these are all functions, rho from x to r plus, such that sum rho x pi x is equal to 1. Yeah, so I'm considering density with respect to pi, which is completely equivalent to considering measures because pi is strictly positive. Okay, so these are the first two objects, and the third object is, well, the Wasserstein metric. Well, in the Wasserstein metric, as I mentioned before, this makes sense as soon as I have a metric on the underlying space. Yeah. So if there exists, or if we are given a metric on X. Okay, so and then of course the question which I would like to ask is, well, if we consider these three objects, do we have again the same result as over there? So is it again true that the gradient flow of the entropy with respect to the Wasserstein metric is the heat flow? So the question, so is the heat flow still the gradient flow of the entropy H with respect to W2. Okay, so let me put this on top. And let me erase this. So to answer this very naive question, well, maybe a good idea to try is to see what happens in the simplest possible case one could ever imagine. So, I need chalk. Here's the chalk. And the simplest possible example, which is actually quite illuminating, is just a space where you have only 2 points. So the simplest possible example is a 2-point space. So we take our set is just say -1 plus 1, and we take now a kernel on this 2-point space. So it doesn't really matter so much what we take. So let's, for simplicity, take this one. So I put 0 on the diagonal and 1 on the off diagonal. So with probability 1, you move from one to the other. So very trivial. Okay, well then one can ask this question. And well, unfortunately, the answer is quite disappointing. The answer is no. So that's bad luck. So why is the answer no? Well, the reason is actually that so there's nothing wrong with the functional, but the metric is not good in this setting. So the Wasserstein metric does not behave very well in the sense that I would like to explain. Maybe if I consider a density, so every density on this 2-point space is of the following form. So you have mass 1 minus alpha to the left, and you have mass 1 plus alpha to the right. Yeah, so remember, I work with densities, so I need to multiply by 1/2, so that's why this sums up to 2. Yeah. So this is a density on a 2-point space, which I call rho alpha, and every density is of this form for some alpha between -1 and +1. Well, you can, of course, calculate what is the Wasserstein metric between rho alpha and rho beta. And what you find is that this is actually the square root of 2 times beta minus alpha. And the reason that there is a square root is because we're working with the L2 Wasserstein metric. So that's just a very simple computation. And this square root is the reason that this space is not good for our purposes. Because this implies that actually this metric space with this metric does not contain any say Lipschitz curves which are not constant. Yeah? And it does not contain any curve of finite length except for constants. So there's no way to talk about gradient flows in this kind of setting if you don't have any nice curves. Okay. So therefore it is kind of reasonable to ask, so maybe we should modify the metric. Yeah? So we should define a new metric in this discrete setting which behaves better than this one. Yeah, so the modified question becomes, can we define a metric on the space of probability densities such that the gradient flow of the entropy is the heat flow, but now with respect to this new metric? Well, on the 2-point space we can now obtain a positive answer. So let me write it as a proposition. So I'm going to define a new metric. So if I take now 2 alpha and beta between -1 and 1, and I'm going to define a metric in the following way. Let me call it curly W. So the distance between rho alpha and rho beta is the integral from alpha to beta, the square root of the arctangent hyperbole S divided by 2S ds. So maybe not the first thing which would come to your mind if you're asked to construct a nice metric. But this, well, this is a metric, and you can show that this metric does what you want. So, so then the heat flow is actually the gradient flow of H with respect to this metric. Okay. So maybe a few words how do you get at such an expression? So what you can do is you can try to guess how the metric should look like. So proof. Let me give you the scheme in one line. So you try as a metric of the form. So you want that the distance between rho alpha and rho beta is of the form phi alpha minus phi beta for some function phi from minus 1, 1 to r. And what you then see is that the mapping which sends rho alpha to phi alpha is actually an isometry from, well, the metric space with this metric to R. And then you can transfer your whole problem, you can transfer it back to R, and on R you can just write down your gradient flow equation, and this gives you a differential equation for phi, which you can solve, and then you obtain this funny expression. So that's a nice game to play. Okay, so at least we have some kind of positive answer, but still we don't know what to do in the general case. So the next step is what can we do in general? So to explain what goes on in general, let's go back again to the classical Rn setting. Because in this setting there is actually another expression for the Wasserstein metric, which is different from the definition, and which actually we will be able to generalize this expression also to the discrete setting. So the formula for the Wasserstein metric in Rn, which you can also give, is like this. So the distance between rho naught and rho 1 squared, you can write it again as an infimum, but now you do not write it as an infimum over measures on the product space, but you write it as an infimum over curves in the space of probability measures. So you say that this is the infimum of the integral 0, 1 of integral over Rn grad psi x dx rho tx dx dt, and it's an infimum over rho and psi. So rho is a curve in the space of probability densities or measures, which has the property that at time 0 it's rho naught and at time 1 it's rho 1. And psi is a vector field. Or no, it's not a vector field. It's a scalar valued potential, depending on time. And they are related in the sense that they solve the continuity equation. So they satisfy the equation dt rho plus divergence of rho grad psi is equal to 0. Okay, and this is actually a very well-known result. This is the Benamou-Régnier formula. Yeah. So the idea is that you consider the infimum over all curves in a set of probability measures, and what you take as a cost is the square of the gradient of psi. And grad psi is this vector field in the continuity equation, which represents the direction in which your mass is traveling. Yeah? So it is again some kind of quadratic optimization problem, but now it's time dependent. Okay. So what we're going to do is we're going to try to find an analog of this formula in the discrete setting. Yeah, so now back to our setting. And we're going to try the following metric by mimicking these formulas. So curly W, rho naught, rho 1 square. And now I'm just going to write down the kind of naive discrete version of this. So this is the infimum over all curves, 0, 1. And now we replace the integral by a sum. And I replace the gradients here by some kind of discrete gradient. Yeah? So just by a finite difference, psi tx minus psi ty square, rho tx. And then I need to take into account our setting, so I need to take into account the k, and I need to take into account the pi. So I'm going to do like this. So that's just, well, there's the integral, so this is dt. So that's kind of maybe a first attempt what we'll try if one generalize that formula. Yes, this is now a double sum, thanks. Double sum x and y. Actually, this is not yet the correct formula, but this is maybe the first try. Okay, so, and we also need to modify the continuity equation, which now becomes something like this, dt of rho x, plus, and then we need to write down discrete divergence and gradients again. So we take the sum over y, there's the grad of psi, so c psi t x minus psi t y, and then there's the rho, and again there's the k. Okay, so, and of course there are the same conditions, like that rho is now a curve in the space of probability densities, and psi is now a function from x to r. Okay, so this is some naive try. Well, the answer is this the right metric? The answer is almost, but not quite. There's still something which needs to be modified. Well, the problem is that if you look at this formula, then you have here this gradient evaluated at x multiplied by the density at x. Yeah. Here we have the discrete gradient, and we want again kind of multiply by the density. But now the density is evaluated, say at one point, so at the vertex, and the gradient is evaluated on an edge, yeah, so in 2 points. So it's not a good idea to write it like this. But what one needs is one needs to replace this by something which takes into account also the density at y. Yeah. So I'm going to replace this by something which I call rho t of x and y, and then define what it is in a moment. But it will take into account the density at 2 points, and here I do the same thing. Yeah. And rho t xy, so rho xy, will be now some kind of function which I call theta of rho x and rho y, for some function which I need to specify. Okay, so that's the metric which I would like to consider. Okay, now comes the theorem, and the theorem says that if you take the right function theta, so if you take the right kind of dependence on these two densities, then you get everything what you want. So theorem, we define theta as follows. So theta of two densities, say of S and T, is the logarithmic mean of S and T. So the integral 0, 1, s to the power 1 minus alpha, t to the power alpha, d alpha. So if we define it like this, then the following holds. So first of all, this W defines a metric. On our space of probability densities. Second, it's not just a metric, but it even defines a Riemannian metric, at least on the interior of this space, so on all strictly positive probability densities. So the metric is Riemannian on P star x, which are all densities which are strictly positive. And third, which is the main point, is that the gradient flow of the entropy is the heat flow with respect to this metric. So the heat flow is the gradient flow of the entropy with respect to this metric. Okay. Okay, so let me say a few things about these results. So one is actually, well, the main difficulty in proving one is actually that this metric is really something finite for arbitrary probability densities. Because that's not completely obvious from this formula, that you can always find a solution to this equation such that this integral gives something finite. But actually, this can be proved, and what you do is you prove it using some kind of comparison argument using the 2-point space. So on the 2-point space, we know exactly what the metric does, and what you then use in the general case is that you kind of compare, say, densities on the general space with corresponding densities on the 2-point space, and then you can then moving mass between arbitrary densities is like iteratively moving mass of densities on the 2-point space. Okay, so second thing, so I said the metric is Riemannian on the interior. So this Riemannian metric actually does not extend in a smooth way to the boundary. Yeah? So it kind of blows up. So the tangent space at the boundary becomes degenerate. So, and what I can also say about 2 is that there's a kind of explicit formula for the tangent space. So remark, and that's also very analogous to the continuous setting. So in the continuous setting, it was well, the observation of Otto that you can regard this Benoist-Brunier formula as a formula of a Riemannian metric. Yeah. So what you do is along this curve, you regard this gradient as a tangent factor, and the formula on top there is then nothing else than the formula of the Riemannian distance. So the same is true here. So the tangent space can be identified with gradients, but now with discrete gradients. So the tangent space can be identified with so the collection of discrete gradients, so gradient phi for all functions phi from x to r. And the inner product on the tangent space is then the following. So the inner product between grad phi and grad psi. So I should say grad phi is here really meant to be a discrete gradient. So it's really phi x minus phi y. So this is then 1/2 times the sum over x and y, phi x minus phi y, phi x minus phi y, rho xy, kxy, sorry, kxy by x. So there's an explicit formula for the tangent space in terms of these gradients. So which is
that's the value of the remaining metric at point rho.
exactly, yes. So this is the metric at the density rho. Yes, thank you. Yes. So this is again very similar to the continuous setting. Okay, so then the main thing which is maybe not so clear is why this logarithmic mean is really the thing which you should consider. So let me give some kind of heuristic argument why this is the case. So why the logarithmic mean? So let's go back to the simple setting of a gradient flow in Rn. If I just have a gradient flow in Rn, so if dt of ut is minus the gradient phi of ut, what you can do is you can differentiate the functional along the gradient flow. So you can compute what is the derivative of psi of ut. Well, and it's very easy to see what it is. So if you use chain rule, then you get grad phi of ut times the derivative of ut, which is again minus grad phi of ut. So this is minus the norm of grad phi of ut squared. Yeah. So this suggests that we could try to do the same in our setting. So we take the heat flow, differentiate the entropy along the heat flow, see what we get, and well, what we get should be interpreted as the norm of the tangent vector. So we can do this computation. So in our setting, so let me introduce the Dirichlet form because it's useful. So the Dirichlet form in our setting of f and g is 1/2 times the sum over x and y, fx minus fy, gx minus gy times kxy by x. So that's the Dirichlet form. So if we now go to our setting and differentiate the entropy along the heat flow, we get the following. So in our setting, the derivative of h along the heat flow, rho t, well, it's an easy computation to show that it is the same as minus the Dirichlet form of rho and log rho. This you can just compute because you know the equation for dt rho is just k minus identity of rho. You do the computation and do some summation by parts and you get this. So if you write out what it means, so this is minus 1/2 times the sum x and y, rho x minus rho y times log rho x minus log rho y times kxy pi of x. Okay, so in this expression you should be able to recognize as the square of the squared norm of your tangent vector. But it's not so clear from this expression that this is really the square of something. But you can write it in a bit different way. So extremely simple trick. So I'm just going to write this as log rho x minus log rho y squared. And then I'm writing rho x minus rho y divided by log rho x minus log rho y times kxy by x. So something completely trivial, I just divided and multiplied it by this difference of these logarithms. But now you can recognize this as the square of some norm, and this expression, so this rho x minus rho y divided by the log of rho x minus log of rho y is actually exactly the logarithmic mean. So this is exactly the same as s minus t divided by log s minus log t. Just a computation. So basically this logarithmic mean shows up because you're trying to do some kind of chain rule for the logarithm here, and that makes everything work. So it's very elementary and simple trick. Okay, so how much time do I still have left?
More than 10 minutes.
More than 10 minutes even. Oh, okay. No. Okay, maybe then. So we are still at the very beginning of all this, but I can maybe mention one application of what one can obtain using this. So in the continuous case, these ideas have been used to prove functional inequalities. So it's our hope that now that we have this, we can also use this machinery in the discrete setting to prove interesting functional inequalities also there. So let me give you one result, and it is some kind of discrete analog of a result by Otto and Villani. So so what Otto and Villani proved was that if you have a measure which satisfies a so-called log-Sobolev inequality, then this measure also satisfies a Talagrand inequality. So this Talagrand inequality is some estimate of the Wasserstein metric from some measure to some reference measure in terms of the entropy. Well, and actually the same result also we also have in our setting. So we can show the following. So if the log-Sobolev inequality holds, well, not log-Sobolev inequality, if the modified log-Sobolev inequality holds, for our kernel and our reference measure pi. So that means the following. It means that you can estimate the entropy of rho by the Dirichlet form of rho and log rho. So this is the same Dirichlet form that I wrote down just a second ago. And now I should make sure that the constants are correct. So if this is smaller than 1/2 lambda for some lambda positive, then the following inequality holds. Then the metric W, so which is now not the Wasserstein metric, but the metric which we considered, so the square of it, of rho, so the distance with respect to the reference measure, so if I write it as a density, it's just, say, the constant density 1. So this is smaller than 2 over lambda times the entropy of rho. So this is some analog of a theorem by Otto and Villani in a discrete setting. So, but I should say that the proof is actually very easy now, because it's actually Otto and Villani already did it 10 years ago, because they had some kind of heuristic argument. So except from giving a rigorous proof of this, they also had some kind of heuristic argument, which would work in a continuous setting if everything were nice and finite dimensional. But in our setting, well, everything is finite dimensional. So in some sense, their heuristic argument gives a proof of this result. So, so the Otto and Villani argument works. There are actually no technicalities, or not so much technicalities to worry about, because everything is just finite dimensional here. Okay, I think that's a good point to stop. Thank you very much.
Questions? Comments?
Actually, I have 2 questions. I'll ask both of them, and then you choose. So first thing, I think there's a classical, another interpretation of the heat flow as a gradient flow, which is if you just take the usual L2 distance between the probability densities, you take the function which is the Dirichlet energy, the unit of the gradient.
Yes.
So yes, is the gradient flow the heat flow for this function?
Yes. So in this setting, the energy would just be this Dirichlet form with f and f, and then the gradient flow with respect to L2 pi is the heat flow.
It doesn't give the same.
Yes, it's exactly the same thing.
Okay.
Yes.
Okay, good. The second question is just one word: curvature. If you have some case.
Yes. Well, this is we are working on in this direction, but I should say it. So this is all very recent, and this is just a first step into introduce this kind of techniques into the discrete setting. So, well, I cannot say much about it now, but this is certainly something which is on the which is certainly part of our program. Yeah.
Is there a way you could interpret this metric as a cost, transportation cost?
Well, not really as you can do it in the classical sense. So in some sense, this is already a formulation kind of in terms of a transport problem. But the difference with respect to, say, the classical Wasserstein metric is that the cost of moving a unit mass depends on how much mass there is already present at the place where you're moving. And so in particular, if you're near 0, then it gets more expensive. But of course, along these curves, this is varying in time. So I don't think you can find another expression for this metric which does not involve some kind of optimization along curves.
This is an infinite. We would like to write it as a
Yes. Yeah, this you can probably do also in this setting. Yes. But I don't think there's a formulation in terms of transport plans like you have for the Wasserstein.
You cannot pick up some cost which gives you this.
No.
Can I ask a very sort of naive question, which is more on the sort of general theme of your talk, and perhaps it's more really relevant for a sort of general discussion. But I mean, in the context of, say, Braskamp-Leib inequalities, where there are sort of several proofs, there's proof by optimal transportation and proof by heat flow. I mean, is there an interpretation of how those proofs relate to each other along the lines of the setting that you're talking about today? Maybe that's not a fair question for you.
Well, maybe. So these the transportation proofs of Braskamp-Leib in the classical setting, they exploit the fact that along these Wasserstein geodesics you have some convexity of the entropy functional or some other functional. So I think if we can prove also in this setting that the entropy is convex for some interesting examples, then there's some hope to prove, well, Braskamp-Leib or other kinds of functional inequalities also in a discrete setting. So, but well, this convexity is something which definitely needs to be clarified in this setting, and this is of course very much related to the curvature question that was asked just before. But we are at the very beginning of this, so I cannot say much.
Is there, well, usually the Talagore inequality has some concentration meaning. Is there a meaning in this formulation, or is it a bit different from the one you expect?
I don't know. I cannot say.
So I think this is a matter. I mean, the usual Talagore inequality. You have a dual formulation, which is a concentration inequality.
Yes.
So, I mean, if you want to see a concentration inequality from this one, probably you need to understand what is the dual formulation.
That's a good idea. Yeah. Yeah. So I can say something about how this relate to. So how this metric relates to the usual Wasserstein metric. So of course we didn't start with a metric on the underlying space to begin with, but the metric which we obtain gives us some kind of metric also on the underlying space, just by considering Dirac masses. So then it's a natural question to compare, say, this metric to the Wasserstein metric, which you obtain by the metric which I just described. And what you can prove is that this metric is always smaller than the Wasserstein metric, which comes from the Dirac masses by this metric. So this does not imply the Talagore inequality in the classical Talagore inequality, because of, sorry?
It doesn't hold in the discrete setting. Discrete cubes or...
Yes, in the 2 points scheme. No, it's not true.
Yeah, one should use W1.
Yeah, this was another question also. I mean,
Yeah.
when you gave your first example of the 2-point space, well, one would be tempted to say, okay, let's keep W1 and let's change the functional maybe. Or
Yes.
did you try something?
I didn't really try. Of course, W1 is also a nice metric in discrete setting, but yeah, so you probably don't get such a nice Riemannian formula like we have here. So.
More questions? Thanks again.